Okay, we're recording. So we're going to just spend as much time as you guys want, just kind of talking about some stuff for the final exam. I've got a review, and it's a Word document. I haven't posted it yet. I'm going to post it right after this, along with I'm going to post this video as well probably tomorrow, because it takes a while for me to get the videos formatted and loaded. So it'll probably be tomorrow that I get this video posted. You guys can review it as much as you want. So you guys will have all that. The test has actually been should have already been opened. I opened it early. Usually it actually isn't technically scheduled to open until I think Friday or Saturday. But I opened it earlier in case anybody wanted to be brave. I don't know why you'd take this one early, but so let's see. We'll start, and I want to share my screen so you guys can see the document. Okay, you guys all should see this as final exam test study guide. All right.
Yes.
So, the test is just going to be the same format as the others. So the final is 30 multiple choice questions, and it's randomly chosen from a bank of about 85 questions. So everyone's test is going to be a little different. It's comprehensive. So this is divided up by topic, and then you have a 60-minute time limit on the test. It's closed notebook, internet, friend, everything. I recommend that when you sit down to take the test, do it in a quiet room where you got plenty of time. Make sure it's the only tab open on your computer, and especially Lisa, where you're saying you're having some internet problems, maybe it might be worth it to look at maybe even going to a library or something where you have a stable internet, just so you don't have it accidentally close on you. And if it does and something crazy happens, email me and I'll get it fixed. But
Okay.
just to avoid any stress for you guys. Let's see, good places to study for this exam. I would recommend, a couple weeks ago, I started doing the Thursday meetings every week, and I've tried to post them all. I didn't get the hurricane and tornado one posted because I accidentally forgot to click the record button. But go back and look at all the other recordings. They're just posted in the announcements. Sometimes they're posted as their own announcement or in a comment to the link to the Zoom meeting. So go back, go through those. Each one of those is about an hour long, and those are really good study guides. They go over the fundamentals. So the way that the tests were written, and again, I didn't write any of these exams, but the way that these exams were written is such that if you understand the basics, the principles, at least the thought is you should be able to extrapolate it and onto the exam with like instances, and I'm horrible at coming up with a question off the top of my head, but it would be something where they're just like, relative to, I don't know. I can't think of anything. Like I said, I'm really bad. But what they'll do is they'll oftentimes ask like a question saying, if you were in this place hypothetically, how does this apply to the science? I mean, it's essentially they're written pretty much the same as the other exams. Now, I'm not a big fan of the other exams. I'm not a big fan of how the tests are written. We'll see how things turn out with the final, but there is a good chance that not only the final, but exam 3 I'll probably adjust the grades. So.
Because it's really hard, or?
Yeah, I just think the exams are really poorly done. And I try to be fair. I think, did I adjust the grades for exam 1? I think I did.
I don't know. I don't know if you did.
And I didn't for exam 2, and I haven't for exam 3 yet. What I'm going to do, basically what I'm kind of waiting to do is see what all the percentages are across all the exams, and then all the final grades are, and then adjust the exams accordingly. So there'll be adjustments at the end of probably right before grades are due, kind of between when the exams due and right when grades are due. Hopefully the day after the test is due, just because I'm going to be out of town the following week. We're going to be going camping in Utah. one last hurrah before we go to Iowa. So there's that. If any of you want extra credit, and this goes for you guys here, or anybody that's watching this later on. There's a couple of things you guys can do. I'm going to post this study guide on the exam or onto the announcements. You guys are more than welcome to go through and basically answer every question. Write up an answer for every question that's on the study guide, and then send that to me. I'll give you some extra credit for that. Another great option for all you guys that you can do as well, you can go on to iLearn or to Canvas, and you guys can look at your exams, and it'll show you the ones you got wrong, all your previous exams, and all you need to do is it'll show you what ones you got wrong, but it won't tell you the right answer. So if you go through each exam, you can write why the wrong answer is wrong and what the correct answer is and why, and then send that into me for all your exams, and I'll give you half points back on all of your questions you got wrong on every exam that you do that for.
Oh, great.
So, if you had a 50%, you could end with a 75.
Okay.
So that's something I like to do. I feel like that's a good way to help too. So we'll do that. There's that. Okay. So any questions on any of that before we kind of take the dive?
I don't.
Okay. Anyone else? Let me check the chat real quick. Okay. Doesn't look like anyone said anything. So, no. Okay, great. Then without any further ado, we'll just go through this. Well, and then what I'm going to do is I'm going to go through this section, of the study guide. And then what I'm going to do is I'm going to ask you guys if you have any questions at the end, and we can go over any questions that you guys may have, just because this might cover some of it. So with plate tectonics, and we're just going to start at the very beginning of the semester. I know this is a couple months ago, maybe kind of hard to dig out of the memory banks, but what are the 3 types of plate boundaries you guys learned about? You guys remember? Good chat.
Man.
Give you guys a few more seconds. Okay, and for those of you just hopped in, I think that was you, Pierre. We're just looking at this first question here. What are the 3 types of plate boundaries?
I found the fault.
Okay. Let's see if you guys can remember the boundaries.
Something's wrong with my sorry, Brother Northrop. Something's wrong with my canvas.
Oh, is
my
it
your my access to your class.
Uh-huh.
They're denying me right now in access.
Oh, you should. Okay. Shoot, I don't know what to do. I will. Have you emailed the anybody about it?
No, not yet. Luckily I was able to post the presentation that I made, but I haven't submitted the presentation to you personally. So
that's fine.
Yeah.
You can email it to me. Do you have an email? Do you have my email? You can just shoot me an email, and that'll be just fine. I'll use that.
Okay, cool.
Until that gets up. And then what I'm going to do, I'll do tonight is I'll email my supervisor, and we'll see if we can't get that fixed for you.
Yeah, thanks.
And I would also recommend you reach out. I think you guys can also reach out to IT for help. So
yeah.
I would also do that. But I will also be emailing people to get you that's weird. I don't know why that's happening.
Yeah, it's first time. I never had that happen to me before.
I've never had that happen to anybody. So
yeah.
Okay, but anyway, we'll get that taken care of, especially since you need to get get on so you can take your test and submit your final presentation.
Yeah, definitely.
We'll get that perfect. Great. Divergent, convergent. So that's two of them. We've got the divergent and the convergent plate boundaries. There's one more, if you guys can remember. Transform. Perfect. So if you guys remember, can you guys remember the direction of movement for a divergent plate boundary?
Mm,
Yeah, away. Perfect. Away. So where is a place in the world where we have a divergent plate boundary where we see this? Let's see if you guys can remember. I know this is kind of old material. It's been a couple months, but what about the mid-oceanic ridge? You guys remember that? That ridge that runs straight down through the center of the Atlantic? Think Iceland, right? It cuts Iceland in half, and Iceland's growing. Let's see here. I'm going to pause the share for a second. Okay. So I'm going to stop the share. Okay. Okay. You guys should see my desktop now, so let's go here. So I'm going to show you the Mid-Atlantic Ridge. Can you guys all see my browser okay?
mhm.
Okay, perfect. So we've got this ridge running right up here. This is Africa, this is South America. And you see kind of this little line right here? This
Uh-huh.
is a divergent plate boundary. And as a matter of fact, right here, this is in Iceland. That boundary goes right up the center of Iceland, and there is literally a crack in the ground where it is spreading apart.
Wow.
So this is one instance of a divergent plate boundary. This place right here is really cool because it's this is fresh water that is filtered through all the volcanic rocks and is supposed to be the cleanest, purest water in the world. But anyways, you can see literally over on one side is one plate and on the other side is another plate boundary. So that's one. Okay, can you guys, can you guys remember now, what's the direction of movement for a divergent plate boundary? Or excuse me, we just said divergent. Divergent's away. So what direction is a divergent plate boundary moving?
Doesn't it go this?
Yep, perfect. Together.
Thank you. Okay.
Pushing into each other. That's totally fine to say together. So let's look at one of those. Divergent plate boundaries. And can you guys think of a place in the world that is a divergent plate boundary? Or I keep saying divergent.
Convergent.
Convergent, thank you. There's a convergent plate boundary. So show you one.
Is this what they're talking about when they say that they make the mountain ranges because they do that? They come together and then they build up?
Yeah, so look at this image right here. You've got the ground, there are these two continents coming together, they're pushing together, and one goes under and one goes above. The one that goes above forms these mountains. So yeah, exactly. That is like a convergent plate boundary. So here's the different types of convergent plate boundaries. You've got oceanic on continental crust. And can you think of somewhere like this? You've got the oceanic crust going down underneath the continental crust, and it creates all these long chains of volcanoes in these mountains. Can you think of somewhere that's familiar that might be a convergent plate boundary where you've got oceanic crust going under continental crust?
Is that kind of like we're around like the Ring of Fire where you're next to the ocean, but
Yeah,
like
exactly.
Alaska or
parts of Alaska, the Cascades, like in Washington, Oregon.
okay.
Another good example for this type oceanic continental collision, that's what I'll call it, convergent boundary, is the Andes. That western border of South America is a convergent plate boundary, and that's what's forming the Andes. And they've got all these big, beautiful volcanoes up there. Then you've got other ones that are oceanic, where you've got two sets of oceanic crust coming together. One goes underneath, one kind of stays on top. They don't really form mountains, other than they'll form land masses from the volcanoes that do form, okay? I'm not going to ask you where somewhere like that. But then you've got, when you've got two continents, two continental crusts coming together. So where is somewhere you can think of like this bottom one right here, where you've got one set of continental crust coming and hitting another thing of continental crust and going underneath? Where's somewhere that could be like that? These make mountains as well. I'll give you a hint. These make very big mountains.
Oh, like St. Helens?
Bigger.
Type bigger?
Bigger. Mm-hmm. You're on the wrong continent. I'll give you one more hint. The largest mountain in the world is
Everest?
Yeah, so where's Mount Everest?
Oh.
Himalaya?
The Himalayas, yeah. The Himalayas are continental collision. That's what's forming them. That's from India running into Asia as it's being rammed into the Eurasian plate. Okay, does that kind of make sense to everybody?
Yeah.
Any questions on those?
So I have a question.
Uh-huh.
So is it possible that at one point or in the future that there is a volcano can be made into within that reaches inland?
Oh, with these big ones? No, they don't really form volcanoes, and that has to do with water. So you can get melt within these just because, think about it, you've got giant masses of rock pushing into each other with extreme force, and it can melt the rock a little bit, but it doesn't melt enough rock to create volcanoes. Whereas up here where you've got the oceanic crust, that's what creates volcanoes. And the reason is because there's water in the structure of the rocks. And as that water is taken down, subducted down underneath some of the crust, it undergoes a process that's called dehydration melting. And that's what'll form the volcanoes. But you need that water. You guys don't need to know that.
Okay. It's interesting though.
Yeah, I think it's really interesting. And that's why there's these big volcanoes where you've got at least some oceanic crust involved. So, any other questions? That was a good question, though. Thanks, Pierre.
Welcome.
Okay, then let's move on to the last one. A transform plate boundary. Can you guys think of anywhere in the world? Well, first off, what direction? How is transform plate boundaries moving?
Let's see, we got the ones that move away, we got the ones that go on top of or come together. I can't remember the transfer.
So think about your faults. Faults have the same directions of movements as plate boundaries. So we've talked about, if you will, with faults, we've talked about normal faults, which are moving away like divergent plate boundaries. We've talked about reverse faults or thrust faults that come together and push against each other, like convergent boundaries. And then there's
Strike
one
slip?
more fault. Yeah, what's the motion of a strike slip?
Up and down.
Yeah, side by side, right?
Yeah, so, yeah, side by side.
Yeah, and so that's the same as a transform boundary. The transform boundary has that type of movement, which like this image right here shows. One side will move one direction and one will move the other. Okay, now can you guys think of a transform boundary somewhere nearby?
Would that be here in California? The San Andreas Fault?
Yeah, the San Andreas lies along a large transform plate boundary. You know, this map right here kind of shows the extent of it. I don't have a really good one here, but yeah, so the San Andreas is a strike slip, a huge strike slip fault system that runs along a transform plate boundary. And I think that's all the time I want to spend on that. Any questions on transform faults
No.
or boundaries?
Well, I'm just scared right now because I'm so close to San Andreas Fault.
Where are you at again, Pierre? I know you're in California.
Hey, I'm in San Francisco.
Okay. All right, and we already kind of answered this second question: which type of plate boundaries produce mountain ranges? But you guys remember, what's the main one that produces mountain ranges?
Not continental, not convert. Is it convergent to convergent, or that makes the big, huge mountains?
Yeah, so just convergent plate boundaries in general will make mountains. Yeah,
okay.
and that's kind of what this question is asking. Just like in general, what type of plate boundaries make mountains? And that's typically your convergent plate boundaries.
Okay.
So the next question is, what are some other features associated with convergent plate boundaries? Now, this is an important question. You get mountains, but what else can you get? So one's a type of mountain, first off. I'll give you an example of one, Mount St. Helens. Or Mount Pinatubo.
So
because they're volcanoes?
That's right. So convergent plate boundaries, many of them, not all, but convergent plate boundaries are also typically associated with volcanoes. Now remember, the continental collisions, those don't really have volcanoes, but anything with oceanic crust has volcanoes. So what we'll say is typically they'll have volcanoes with convergent plate boundaries. Now there's another thing. We've got volcanoes, but we have one other thing that talked about in this chapter that are associated with plate boundaries, the convergent plate boundaries. Give you guys a couple of seconds to think about it, see if you guys can remember.
Earthquakes?
So you can have earthquakes, but what type of features? Okay, ready? You get oceanic trenches.
Oh, I wouldn't have remembered that.
Yeah,
so
I would have guessed.
I wouldn't have remembered that.
That would have been like way
a little too far
beyond my memory.
So if you guys remember, you've got your subduction zone right here, and you've got one slab going under another. And what happens is that as it pulls down, it kind of depresses the lip of the other slab as well, and it creates this big trench. So remember that. You'll want to remember that because I know one of the questions in the bank that they can select from does ask about oceanic trenches.
Okay.
So know that they can have oceanic trenches. Okay. And, any questions on plate tectonics?
Mm-mm.
Nope.
Okay. I think anyone in the chat, any questions? Okay. I think we'll move on. And if I see a question come up, okay, great. And if I see any questions, more questions come on, we'll stop and address it. Okay, so earthquakes. What type of fault is usually found at the base of the mountains in the western United States? You guys see if you remember this. And first off, what are the different types of faults again while we're thinking about this? We've already mentioned them. So what's the type of fault that goes away, that spreads apart? Well, not spreads apart, but slides away.
Divergent.
That's the plate boundary. We're talking about faults. It has a different name.
Oh, is it the thrust?
Other one.
Let's see, there's strike slip fault, and there's dip slip fault. Normal.
There you go. It's a normal fault.
Normal.
Oh.
So normal faults slide away. Can you guys see me? Have a little image of me talking on the side at all?
Yes.
Okay. So you see my hands. Normal faults slide that way. They go apart like this.
Oh.
Okay. So that's a normal fault. And a good way to remember a normal fault is it's normal for it to slide away. That's one way I kind of remember it. Now, what's the other type? So we've got a normal fault, we've got a thrust fault. You mentioned that earlier, Lisa. What direction does a thrust fault move?
It's like a hanging wall.
Okay, so you've got a little bit. We'll go over this again. It's been a while. So on your faults, you've got your hanging wall, which is the wall that if a miner were to do a mine shaft straight through, it would be the wall he could put his hands on and hang from. Okay, so this is his hanging wall. And then you've got your foot wall, which is where your feet are if you're walking through it, right here, if there's a tunnel going through right here. So on a normal fault, your hanging wall goes down relative to your foot wall. Okay, that's that pulling apart that we were just talking about. On a thrust fault, your hanging wall goes up relative to your foot wall. So again, remember the top is the hanging wall. It's the wall you could hang from. Your bottom is your foot wall. That's the wall your feet are on. So thrust is up. Normal fault is down. That makes sense to everybody?
Yep.
Perfect. Okay, so then if that's the direction of those, what's the direction of a strike slip fault?
Up and down.
It's not actually up and down, it's sideways.
Oh, sideways.
Yeah, it looks like up and down because I always show it this way, moving like this. But if you were actually to look at it, it's going to be that way, moving this. You can have left lateral or right lateral movement, which is just the movement of the fault. You don't need to know that. Okay, so with those three different faults in mind, a normal fault, a thrust, or reverse fault, can be called either, and a strike slip fault, what type of fault is usually found on the base of mountains in the western United States?
Strike slip faults.
There's some, but that's not the predominant one.
Are they the normal?
That's right, normal faults. Normal faults are typically at the base of the mountains all across the United States. So for example, at least here in Utah, we've got that beautiful Wasatch Front going all, north and south. And, along at the base of the Wasatch that follows up basically Utah County. So from Payson and Santaquin all the way up to the north through Salt Lake and up into Davis County where you've got, Bountiful and all that, you've got these big normal faults. They're part of the Wasatch Fault System. As a matter of fact, those big normal faults run all along the mountains, the Wasatch Mountains, all the way down into southern Utah. So that's just kind of an example of one location here in the western United States where you've got these big normal faults. along the base of the mountains. Okay. Now, the largest earthquakes, I'm skipping one for now. I'm moving down, I'm not going to talk about liquefaction yet. I want to talk about this one here. The largest earthquakes happen at what types of plate boundaries, you guys, or what type of plate boundaries? You guys remember?
What type of plate boundary? Isn't it the convergent?
That's right. That's where the biggest earthquakes happen. And a good example of that is the Ring of Fire, right? So you get Japan, for example, how many big earthquakes does Japan have? We're always hearing about them. You know, the Sendai earthquake and subsequent tsunami was a massive earthquake that happened along a convergent plate boundary. So these are really, really big. Now, these earthquakes that happened just recently over in California, these occurred along what type of plate boundary?
Is that the transfer?
Yeah, transform. Or
transform.
So that was along a transform plate boundary where we had strike slip faults. As a matter of fact, it was a strike slip fault that ruptured that caused all the earthquakes in Ridgecrest, California. And the largest one that we saw there was a 7.1. That was the big one. Now, that's still a really, really big earthquake. But the last big earthquake, or the Sendai, Japan earthquake, or we'll use one of your case studies, for example. The one that happened in Kobe, I think it was bigger than a 9.0. So for perspective, a 7.1 is 10 times, or a 7.0 is 10 times greater than a 6.0. And an 8.0 is 10 times greater than a 7.0. So that means that a 9.0 earthquake is 1,000 times greater than a 7.0 earthquake. Did I do that right? No, 8, 9, no, 100 times bigger. So, you know, the earthquakes that happen along these convergent plate boundaries are very, very big earthquakes. Okay, now we'll go. Do I want to talk about liquefaction? Let's see. Seismic engineering, the two largest earthquakes on record. Which case? Okay, so what is the difference between epicenter and hypocenter? Do you guys remember that from an earthquake?
What is the epicenter?
Great question. Let's go here.
The hypocenter, isn't that like where it starts, like where the initiation of the earthquake, like where it starts underground?
Yes.
That's what I remember.
Yeah, you nailed it. So let's go to this image right here. Here's your fault, this line. Your hypocenter is where the actual break happens. And then the epicenter of your earthquake is the surface, directly above on the surface the point on the surface that is directly above where the actual break happens. So does that kind of make sense? Does that make sense to everybody? Your hypocenter is underground typically, and it's the exact location, the exact point where the rocks broke and all the shaking started. The epicenter is the point on the surface that is directly above that. We all good there? Is any questions on that?
All good.
Okay. At any point, anyone has a question, please just shout out, stop me. We'll look at it when we can talk about it. Here's another good example. Good figure to look at. Here's your hypocenter in the center. This is where all the waves, remember the S waves and P waves, this is where all they all come from, is this hypocenter right here. The epicenter is directly above it. So if you look, epicenter will not feel shaking at the same time a hypocenter does, unless the epicenter and hypocenter are at the same location, which can happen. Now, granted, the epicenter typically feels shaking like milliseconds after the hypocenter because how quickly they move. So, okay. Great. So now let's go back up to liquefaction. What is liquefaction?
What? Liquefaction.
Can you say that again? Okay. So let's go here. Sorry, guys. And I know I like to flip around a lot. It's because I like images to show you. Okay. So here is an example of liquefaction. So if you guys remember, this typically happens on soft, unconsolidated soils, you know, sandy stuff and whatnot, that has water in it. And as the shaking starts, you know, it kind of, the water is pushed up in between all the different clay minerals and those different things. And it creates it so it's not solid anymore. It's got space. And then things can sink down into it. So right here, what happened with this car is it was parked right here. Just a second, buddy. Good night, bug. It was parked on some clay. The shaking happened. The water got in, and it acted like quicksand, and like super quicksand, and the car just sank straight in. And then the shaking stopped. The water retreated, and it solidified again. Does that make sense to everybody?
Yeah, I don't remember that from the first time. Can't remember that.
So liquefaction, this is something that'll definitely be on the test. Great pictures showing you what liquefaction does.
So it's just, so like if I have to explain it on the test, it's kind of like a quicksand?
That's a good way to think about it. It's, just think about it as you've got your, imagine my hand are two grains, you know, like sand grains or something, and they sit next to each other like this when there's no water in there. And they're solid. They kind of anchor onto each other, and you know it'll support weight and everything. But all of a sudden, you introduce water, and they kind of float apart. And then someone will step on this, and there's nothing supporting it, so it just sinks. Does that kind of make sense to everybody? Okay, so, and it's really dangerous. So like right here, this image is showing what liquefaction can do to buildings. Parts of these buildings, their foundations have actually sunk and they've fallen over. You guys can see that there. Let's see if I can find liquefaction house. Here we go. So here's a good example. There's a famous one in the San Francisco earthquake in the early 1900s, where this house is literally started to sink from liquefaction. So make sure you know liquefaction. Spend some time going over that, all you guys. Okay, so any questions on liquefaction?
Nope.
Okay.
What type of material does liquefaction happen? Is that where we just write the clay in the water?
Yeah, it's typically your clays, your lake bed sediments and sandy sediments. It's your loose stuff. You know, it's not going to happen on hard rocks and things like that. Really rocky stuff.
Mm-hmm.
I have a question. So usually liquefaction happens next to like a bay or something, like near like an ocean.
Great question. So let's see. Oh, I wish I'm not going to pull up the case study because I'll just take too long. But if you guys look at the case study from, I believe it was the Kobe, Japan, they've got this really cool figure in the case study that the group put together, and they show all the man-made sections of the island, or of part of Kobe. And these regions, what they did is they basically just brought dump truckloads of dirt and just built out the shoreline until it extended out further. And it was just on this loose dirt. I mean, they compacted it, but you know, it wasn't liquid or lithified into rock. There was no rock. It was just dirt. And then what happened when that big earthquake hit Kobe, Japan, all the liquefaction occurred there because it was this loose, unconsolidated sediment. And so that's kind of the same thing that you'll see at, you know, that's what the kind of the key is for liquefaction is loose, unconsolidated sediments. It can be silty, it can be clay, it can be sand. A beach is a horrible place to be on when there's a big earthquake going on. So that's kind of what you're looking to be away from. Does that kind of make sense to everybody?
Yeah.
Yeah.
Great. Okay, we'll keep moving then. What are some examples of seismic engineering? Now, seismic engineering, what we're asking is like the different type of building things that people do to help buildings withstand earthquakes. So can you guys think of some seismic engineering? Show you guys some. So this is a really hard one to see, but it's pretty cool. This building they're showing here, this is the foundation. And this foundation is, if I'm looking at this one right, this foundation is such that it can move.
Oh, like the temple, like the Salt Lake Temple?
Exactly.
Ah,
You know how the Salt Lake Temple's on the big rollers?
yeah.
Basically, this is an example of seismic engineering where all the shaking is going to happen. Your building sits up here on top, but it's on rollers, so the shaking happens underneath it. And the building experiences minimal shaking.
Oh.
That's a good example of it. Let's show you another one. Oh, this is good. You can see those rollers right here. This is on kind of springs. And the springs will kind of move with the earthquake, and there'll be minimal movement in the building itself. Right here, they'll put these big cross beams going up buildings, and that'll significantly strengthen walls to help them withstand earthquakes. There's a lot of really, really cool stuff. For example, my parents' home in California is built to withstand up to a 9.0 earthquake, and they've got in each corner of their house, they have these big brackets that are like a foot tall, and they're shaped like an S. Or not an S, but kind of like a squiggly line. And so the walls are mounted on these big S brackets, and as these, I say S, but like I said, these squiggly brackets, and as shaking happens, those brackets can move with the foundation, and the walls can stay perfectly fine. And it was really interesting because there was a lot of really heavy shaking in the earthquake the Ridgecrest earthquake when we were there, but everything was totally fine. It was actually helped the house. There was like there was no damage, and like I didn't see pictures shaking or falling off, which you would normally see in a 7.1 earthquake, because those big brackets gave the mobility to the house and the foundation. So the shaking in the house was actually less than the shaking was outside. It was really weird because I was sitting there watching my blinds shake a little bit. I went outside while the shaking was still occurring, looked at our cars, and our cars were shaking far worse than our blinds were. And that's because of the good seismic engineering of those brackets.
Mm.
So those are some good examples of that. Okay, here's a good one. Where can earthquakes happen in the United States? Where are some places that are prone to earthquakes in the U.S. other than California and San Andreas?
I was about to say.
Yeah, I thought I'd be preemptive and make it a little harder.
Alaska?
Oh yeah, great. Alaska is a place that has a lot of them. When I was little and my family lived in Alaska, we felt them all the time. Where's somewhere else?
Does Yellowstone have a lot?
Yeah, Yellowstone does have earthquakes. Yellowstone's earthquakes are typically associated with a big supervolcano and other things in there. But great, earthquakes in Yellowstone. Where else? You guys remember the New Madrid case studies? So you can get earthquakes over in like Missouri. There's a failed rift there that can cause earthquakes. You'll have to go back and review your case studies because one of the case studies occurred in Missouri. So you can get them in Missouri, and of course there's Utah, you know, basically anywhere from California all the way out to Colorado. You can get earthquakes. Okay, I would spend some time. I'm not going to tell you this. I want you guys to go research it. The 2 largest earthquakes on record. Go look that up. And then this, I'm not going to talk about either. You guys can do this on your own time. Which case study earthquakes had the highest death tolls? That is a question on there that you can get. So know which case study had the highest death tolls. The other thing you should know for the test is which case studies are the most costly. Okay? And that's not just like which earthquake's the costliest earthquake, but know like overall, out of every case study we've gone through this semester, which one's the most costly, and also know which one was the most deadly. Now, the most deadly one should be easy. Okay, that one should be really easy because this one had like millions of people that died. Out of curiosity, can any of you think of that case study? Can any of you think of that one right now?
And we're not talking about just the United States. We're talking anywhere.
Yeah, this is of all the case studies we've done this semester.
Was that Pompeii?
Nope. Far worse than Pompeii. And it was not an earthquake or a volcano. It was the China 1931 flood. Okay, that one had, I think, that one had like tens of millions of people that died. And that was not necessarily because of drowning initially. That was because of disease and starvation. So, know those, okay? Where in the U.S. did 3 large earthquakes happen in a short amount of time? That look up yourself as well. It's one of the case studies, so go through the case studies. And then where was the largest earthquake in European history? Again, another case study. So go back, spend some time on the case studies, okay? And I'm not going to spend time on those. I'm going to post another document for you guys where it has all the questions about that each case study is supposed to answer with the answers to facilitate it being really easy for you guys to study. And that'll help with this as well. But go through the case study presentations as well. It'll be a lot easier to remember if you're going through the presentations and looking at pictures, and you can put pictures and things like that to the data. So we'll move on to volcanoes. Anything else on earthquakes? Okay, we'll hop over to volcanoes. What are the different types of volcanoes and how are they identified? So can you guys remember the different types of volcanoes? And pull this back up.
I remember the strato.
Yeah, stratovolcano is one. How is that identified? What's kind of the key defining things of stratovolcanoes?
They're like the ones that are really big. I remember because the Pinatubo one.
Yeah.
Yeah.
Perfect. Yeah, and that should be easy for you to remember.
Yeah.
Right?
So
They're the big conical mountains, like kind of that quintessential volcano that everybody thinks of. Right? The big dome that sits up there, and when it blows up, it blows everything up and just really explosive. Great. So that's one, the stratovolcano. It has another name, can also be called a composite volcano. So what's next? What type of volcano is Hawaii? See if you guys can remember. Like Mount Mauna Loa and Kilauea. Okay. Remember, it's a shield volcano. And remember, the shield volcanoes are actually technically the largest volcanoes. They're just not steep. I'll show you a picture of a shield volcano here. And remember, shield volcanoes aren't super explosive, or they're very eruptive, but they're not super explosive. So here is a big shield volcano. You can see big gentle slopes going up and then kind of reaches the summit, the peak, and then gently slopes back down, right? They look like, and they're big discs, they look like a shield. Okay, so this is like the Hawaiian volcanoes. They don't blow up half the mountain. They spew a lot of lava oftentimes. You know, when you think about Hawaii, that's exactly what a shield volcano acts like. And actually, the largest volcano in the world is a shield volcano, which is Mauna Kea, because Mauna Kea goes all the way down to the seafloor. Okay, so we've got that. We'll look at this image here. Oh, I must have gone back. Types of volcanoes. Okay, so we got here stratovolcano. You've also got a lava dome, kind of the same thing as a shield volcano. Say that again?
A cinder cone?
Yeah, you've got cinder cones. Perfect. See if we can find a good image of a cinder cone. Here we go. So you got these cinder cones. Let me pull up a cinder cone volcano. So here's a cinder cone volcano. They are kind of tall and peaked like a stratovolcano, but they're very different in size. They're significantly smaller. You know, a cinder cone volcano can be only a couple 100 feet tall, right? And when a cinder cone volcano erupts, that's what it looks like. It's not blowing the whole mountain up. It's literally blowing cinders up into and ash and spewing lava up into the air. So this is kind of a cinder cone. And then you can get lava domes, which typically can happen on shield volcanoes, but it's a big dome that starts forming and pushing up as lava forms underneath it. Let me show you a picture of a lava dome. That's a lava bubble. Here is a lava dome. This is the lava dome of, I think, Mount St. Helens. So this is a big dome where underneath is a bunch of lava. Now, not like in the dome, but it's way down beneath. There's a bunch of lava. Or magma. Remember, magma is what it's called while it's still in the Earth's surface, or in the subsurface. Okay, any questions on those? Okay, we talked a little about where volcanoes occur, right? They typically occur along convergent plate boundaries, and they can occur on divergent plate boundaries as well. Anywhere where and that happens along divergent plate boundaries when the crust, everything's pulling apart far enough, the crust gets thin enough that you'll actually have magma right under the surface that'll melt its way through. That's like why there's so many volcanoes in Iceland. Okay, what are some signs that a volcanic eruption is about to occur?
There's like some earthquake.
Yep, I heard someone else before too, and I couldn't hear you very well. It was really quiet.
Oh yeah, because I was thinking.
Oh, okay, perfect, Karen. So, yeah, earthquakes. You can get earthquake swarms. So Mount St. Helens had big swarms of earthquakes happen before the eruption. I think Pierre didn't Pinatubo as well.
Yep.
Yep, most do. What's another thing? What do volcanoes release a lot of?
Yeah, I was about to say, isn't there a lot of gas released?
Yeah, exactly. So you can get a lot of gas release right before a volcano erupts. That's a big sign. So a lot of times what scientists will do, geologists will do, is they'll also have monitors on the volcano that will measure not only earthquakes, but they'll have monitors that or devices measuring gas output. And they'll be like, oh, wow, we're seeing high spikes in, sulfur dioxide and all these nasty gases associated with volcanoes. So that's one good way to look for that as well. Those are kind of the main ways. Can anyone think of any others?
I was thinking about vents.
Uh-huh. You can get vents where it'll shoot out some gas. You can even get vents that'll release out a little bit of lava before the main eruption happens. The other thing you can see is you'll see a lava dome growing. You can see the lava dome expanding a lot. And sometimes you can see landslides as a precursor to an eruption. A good example of that was Mount St. Helens. The landslide happened, and then the volcano blew up. Does that kind of make sense to everybody? Any questions?
No.
Okay. Now, hotspots. Can you guys remember what a hotspot is?
So why is a hotspot, and is it called a hotspot because it is constant? It has lava constantly flowing.
Close. And you're right. It is a hotspot. And what's going on is we get what these called, let me find a good one. This is a good enough image. We get what's called a mantle plume. We don't understand why they happen really, but it's basically this big plume of rising hot magma. And it rises, melts through the surface, and creates these volcanoes up right here. There's no plate boundary there. There's nothing. For whatever reason, there's just this really hot pillar of rising magma. And that'll create will often create these big shield volcanoes out in the middle of the ocean for nothing. There's also a big hot spot under Yellowstone. That's what's created Yellowstone. So that's, you're real close. And that was real good. And that's exactly what Hawaii is a big hot spot. Does that make sense to everybody?
Mm-hmm.
Perfect. Any questions on hot spots?
No.
Okay. All right. Biggest volcano on Earth. I would research that one yourselves. Here's a good one. What makes some volcanic eruptions more explosive than others? This is something you absolutely need to know.
Does that have to do with the consistency of the lava?
Yeah, exactly. And can you remember in specific what it was about the consistency?
Is it higher amounts of silica?
That's one. Perfect. So the more silica you have in a magma, the more eruptive your volcano will be. There's a couple of things that go into this. So there's another thing. There's two more things in the magma that can make it more eruptive. Can you think of any others?
Let's see, because I know if the lava is thicker, then it tends to hold the gas in more.
That's right.
And that can cause it to be more explosive.
Perfect. And that's called viscosity, right? Yeah. And so the more viscous, and this is viscosity as a refresher, is a measure of, and I like to put it this way, syrupiness. The more syrupy it is, the more viscous it is. So these volcanoes that are really explosive have a thicker, more viscous magma and lava. And that, like you were saying, it encapsulates the gas a lot more, and the gas can't escape. And more gas builds up until finally, like a shaken up soda bottle, it'll explode. Perfect. And then the last thing is water. The more water you have in it, the more explosive it is. And that's because the hotter, as it gets hot, the water vaporizes and becomes a gas. So perfect. You got all three of them. Okay. So we'll leave that one there. Any questions on that? Okay. Now, what is the greatest threat if Mount Rainier were to erupt? Can you guys remember this? Think about your guided lab.
The guided lab on that was the movie, right?
So there was that, yeah, and it also talked about a town of Ording. You remember all the stuff with Ording?
Oh, yes. Oh, was it the Lahars?
Exactly. So the biggest threat of Mount Rainier is the Lahars. And can you explain what a Lahar is for me?
So the Lahar would be created from, so if the volcano exploded,
Mm-hmm.
the lava would melt all the ice that was on the mountain, and as it traveled down the mountain, it would gather more stuff and become kind of a mudslide
Yeah.
kind of thing. And then it would just keep gathering materials, and then it would flow down the mountain, and more than likely it goes into like riverbed areas.
Yep.
It will flow along and can get up to 40, 50 miles an hour.
Perfect.
And it can wipe out those towns that are on the low elevation close to those river areas.
Perfect. You nailed it. That is exactly what it does. Like, perfect. You can also, one extra thing I want to add on to here is you can get lahars without an actual eruption. And that can be kind of a precursor to the eruption. As the ground's getting really, really hot from the magma rising and being right there about to explode, it can actually melt the ice, start melting the ice even right before the eruption. So let's show you some pictures of lahars. You know, it looks essentially similar to a big mudslide, or debris flows, more accurately. A big debris flow coming through, and they just rip through these towns, and they'll bury them sometimes in 10s to 20s, feet of mud and debris. So these are very dangerous. Just a sec, guys. But there is a charger on the counter. It's the corded one. Do you see it? It should be there. I picked it up and put, check in our room. I know. I'm sorry. Okay, good. You taking some stuff to the storage unit? Okay, love you. Sorry, guys. As I was telling some people earlier, we are moving next week, so we're kind of busy. The house is filled with boxes. Okay. Okay. Pyroclastic flows, another thing I want to talk about. There's not a question there on the study guide. And for those of you who've come in since we've started, I'm posting this document tonight for you guys, so you guys can go back through it on your own. But we've got pyroclastic flows. Do you guys remember what a pyroclastic flow is? I'll show you a dramatic picture of one. See if anyone remembers.
Dense and destructive mass of hot ash downslope.
That's right. So you get this hot ash that gets erupted up into the atmosphere right from the volcano. It gets spewed out, and it goes thousands and thousands and thousands of feet, even, hundreds of feet to thousands and thousands of feet up into the air. And this hot ash, as it goes up, it starts to cool. And as it cools, its density increases. So then it comes flowing back down, and like this picture here, it rockets down the side of the mountain at speeds sometimes greater than 100 miles per hour. Now, what's so dangerous about these pyroclastic flows is, I did say they cool and then they fall. Yeah, but you're right, Karen. They're still incredibly hot. If you get caught in a pyroclastic flow, you will not survive for the most part, because it is so hot still. I think the inside of them are still hundreds of degrees Fahrenheit.
And isn't there a lot of gas that would be poisonous to us anyway?
Yep, exactly. It's also filled with all sorts of nasty volcanic gases. So pyroclastic flows, a great example of a pyroclastic flow is Pompeii. Pompeii is buried under like 30 feet of ash, and a lot of that came down through a pyroclastic flow. And then a subsequent ashfall after as well. But Pompeii and Herculaneum were both hit with big pyroclastic flows as well. Okay. Okay, know this. Which case study eruption caused a year without a summer? Know what caused the eruption of Mount St. Helens? I mentioned that earlier. And I just mentioned this. What volcano, well, know this. What volcano buried Pompeii? And then also know which volcano may have begun the legend of Atlantis. Now I'm going to talk about these two here because one of these case studies was a case study provided you guys, a presentation provided you by us. No one did this, but it was on one of the European volcanoes. So who remembers what volcano buried Pompeii? Anybody?
I believe that was Vesuvius.
Yeah, Vesuvius. And you guys remember which one started the legend of Atlantis?
No, but I do remember we have the document somewhere.
Yeah.
In our past weeks that has all that information on there. So I do remember reading about it, but I don't remember which volcano it was.
Okay, so that's Santorini. So, and that's perfect. Yeah, and that document is still in the announcements. If you just go back, that'll be a good one to study from. And then I would also recommend going through all the case study presentations, and then you can also access this presentation on Santorini just in the week 6 case study module. But Santorini, so Santorini's in Greece, and Pompeii was in Italy. Okay, with that, any questions on landslides? Or landslides, we haven't gotten to landslides, volcanoes. Okay, then we'll hop down to landslides. And sorry, if you guys need to hop out at any time, you're welcome to. I'm just going as long, I'm trying to do just a good review to help for the test. And this video will be posted, so, because I know we've been going for, coming up here in about 15 minutes on an hour and a half. So, landslides. What are some different types of mass wasting and how are they identified? So what are some different types of landslides that you guys can remember?
Sorry, my speaker was off. Are you talking about rotational landslides and transitional landslides?
So yeah, you've got translational. That's right. Mm-hmm.
Oh, translational.
And the rotational one. What's another name for a rotational landslide? You nailed it. There is one called rotational, but it has a more common name.
The slump?
Yeah, a slump. So you've got slumps or rotational, translational. What else do you have?
Block slide.
Yep.
Block slide. Uh-huh.
Rock fall.
Uh-huh.
Creep. Flow.
Creep. Yep.
Mud flow.
Mud flow.
Earth flow.
Earth flow. Very good. And then you've got debris flow and all sorts of different ones. Great. You guys identified those. Let's go. I'm just going to go over a few of these for a more in-depth view of kind of each of the main types of landslides. Go back to the week that we went over landslides on the Thursday meeting. The recording is posted in the announcements, and you guys can go there, and I go through each one. We look at videos of them and pictures of them, and we talk about them. So that's a really good place if you're kind of unsure how different things look and what's the difference between an earth flow and a debris flow and a mud flow. I highly recommend going back to that video. It's just in the announcements. But I want to go through a few real quick. So we'll start with debris flow. And I'm going to show, we're actually going to go to YouTube for this. Because I think it's easier to understand these actually seeing them happen. So just give it a second. Debris flow. Okay, and we will do, let's do an exciting one. It's kind of a debris flow. We'll look at this one first. So you can see this is a debris flow. You see all those huge boulders in there? And you can see it's flowing like a river, but it's carrying all sorts of different debris and stuff. And everyone can see the video, right?
Yep.
Yes.
Okay, perfect. So this is a good example of a debris flow. Super fast, super strong. Not the most violent of ones that I've shown in videos of, but you can see it's got all sorts of debris in it. I was hoping it would be sooner. I wanted to show you guys there's a car that comes down. Kind of just interesting to see. But anyway, the big point was right here when you see all these big boulders. So that's characteristic of a big debris flow. It's got all sorts of debris. Now let's look at a mud flow. We can see the difference in a mud flow. So this is in Swallows Desert Road, wherever that is. Oh, we've got a ad. A second here. There we go. Okay. No thanks. So this is a mud flow. And you look here, it flows really good, but it's pretty much all just mud coming down. There's no big boulders and stuff like that. Yeah, it'll pick up some trees and stuff, but it's more just like a big river of mud. You guys kind of see how it looks a little different?
Yes.
Looks watery.
Yeah, it looks more watery, and I guess the word is more homogeneous in its makeup, not so many big boulders and things like that. It's more just kind of super ultra muddy water or watery mud. I don't know, one of the two. So, and then the afterflow of this will just leave big compact mud everywhere. Whereas a debris flow, there would be big scattered boulders and all sorts of stuff like that. Does that kind of make sense to everybody?
Yes.
Yes.
Okay, now let's look at an earth flow. I like this one in Mongolia. It's just really cool. So this is an earth flow, and you can see this looks very different than the mud flow. First off, it is, come on, show me directly on it. There we go. It is a lot more it's a lot less watery. It's still flowing, but it literally looks just like the whole earth is just kind of flowing down the side of the slope. Okay? So this is a big earth flow. Okay, and I think that's all I want to show you guys in that. So now I'm going to show you guys a picture of creep. Creep is important. The creep is particularly important if you're looking to buy a home on kind of a hillside. You'll want to look for creep. So who remembers, who can explain kind of, oh, let's look at, not creep radiohead, we want creep mass wasting. Okay, here we go.
The
So,
note that I have is that the ground is slowly moving down.
Yep.
Slope. It freezes, thaws, and moves down.
Yep.
Freezes, thaws, and moves down.
Perfect. You get the freeze thaw. So as it freezes, the water will cause it to expand out. It thaws, it shrinks down. And as it expands, it just kind of slips down a little further each time. And a great way to look for creep is, this is really slow. This happens over years, is you look at the trees and you see this tree right here, how it's bent. This characteristic bent shape, you'll see it in tilted fence posts and all sorts of stuff, is indicative that creep is happening here. And creep oftentimes is a precursor to another major landslide. Okay? Okay. Any questions on creep or any of the landslides we looked at? Okay.
No.
All right, we'll keep going then. What are some causes of mass wasting that you guys can remember from the reading?
High moisture in the soil.
That's right. You get it really moist, it gets heavier, and the stuff isn't packed as tightly together because it's got water in between. It's really easy for it just to slide on down. What's another one? So we got moisture. That's a great one. What's another one?
So I know that the type of soil matters also, because if there's a lot of clay in there, then it's also more likely to slide.
Yeah, perfect. Your clay content. Clay is a really weak layer. It's really easy for it to fracture and break along or slide along a clay layer if you've got heavier stuff on top. Can you guys think of any other things that can cause it?
Melting snow.
Melting snow, just adding moisture into the ground. For example, and this is often caused by us, undercutting. So when, let's say we make a big road cut in a mountain pass, and all of a sudden there's not as much support for the stuff up above, that can cause a landslide. And there's one more thing. It's the big thing is the angle of repose. You guys remember what angle of repose is?
Is that 34?
Yeah, it's about 32 to 34 degrees. It's kind of this optimal angle. Anything hot, that or higher is prone to sliding. Anything less prone to sliding. So just kind of the angle of the slope is a major contributing factor to landslides. So what are some ways we can prevent mass wasting?
So providing means of being able to drain water off of the mountainside.
Yeah, that's a great one.
So I know that one of the problems can be if like we build structures or roads or something and it ends up keeping the moisture from escaping.
Yeah. Yeah, so making sure everything is properly drained, that is a huge thing. Anyone think of anything else? So what about, let's look at a couple here. We'll show you some pictures. This might help.
So I think terracing is one of them.
Yeah. Terracing.
Yeah, rock wall, graded.
Grading, yeah, terracing and grading, rock walls. A lot of times what they'll do too is they'll pour cement over. I don't know if they're going to have any really good ones looking in here, but they'll pour cement over kind of these areas that are prone to landslides. They'll put giant fences with these huge like rebar mesh kind of thing to catch boulders as they fall, or they'll even put just big like nets, metal nets over slopes to hold them down. But there's another really big one, and it's probably one of the easiest. Plant plants, particularly grasses. So by putting good plants with deep roots, we can help mitigate against landslides because those roots will help kind of give the soil something to anchor onto. Okay, so know this. Which case study landslide was the most deadly? You can research that just going through, okay? Any other questions on landslides? Okay, and I highly recommend you guys go back in preparing for the final. Watch the video where I go over the landslides. We go through all the PowerPoints, and I spend probably, I think, a little over an hour just talking about landslides. It's good information, be really helpful with the test, and make sure you're spending plenty of time with your study guides. Okay, floods. Where does the most erode? Okay, first, before we talk about meandering river, what is the difference between a braided and a meandering river?
Isn't the braided one, well, meandering is slow and it just kind of goes like a snake, and the braided one spreads out because there's so much debris in the river that it just kind of goes everywhere around it.
Perfect. So we'll look at a big meandering river first. So these are, go ahead.
It was the amount of silt in the braided river, right?
That's right. The braided river has far more. That's right. So you got these big meandering rivers here, right? They're slower moving, not a lot of silt and stuff in them. And they just kind of flow and meander their way on down. Then you've got these big braided rivers, which are really cool. And these just have a ton of silt. They can be a little faster moving. They've got all these little channels going everywhere. So these are your big braided rivers. And a lot of it has to do with sediment load, which I'm just talking about how much silt is in the river itself, right? Or mud or whatever, right? So there's a lot of silt in suspension here. Okay. Now, oops, here's a really cool picture of a braided plane, but I didn't mean to show that. I wanted this one. So who can tell me, you've got your braided river right here. From right here where the tree is, all the trees are on this right side, over onto the left side, the trees on the left side. What is that expanse called?
Nut bank? Or is it
Point blank?
point bar?
No, no. If you're thinking meandering rivers, this is a braided. This will be on a meandering river as well. But what you're saying, the cut bank and the point bars, those are simply just on meandering rivers. So from here,
the floodplain.
That's right. This is the floodplain. This is the area that floods, and in theory, it could go up over that. But this is your natural floodplain right here. Let's look at a floodplain on a braided river or a meandering river. Floodplain. Boom. Okay, let's see if we have an actual picture here. Not sure I like many of these. They're just hard to see. It's a little hard to see on meandering rivers. So what I'm going to do is I'm going to use this. So you got your meandering river here. You've got your kind of bluffs over here and over here, or levees. This is kind of your floodplain right here. Got your little natural levees here, but you got your big floodplain right there. And that's kind of the extent that when it floods, it gets to. When you get really, really, really bad floods, sometimes it can go further. Okay, good. Now, Karen was bringing up that you've got point bars and cut banks. So let's go point bar. Look at an image of this right here. Oh, it's small. I was hoping for bigger. That's okay. We'll work off of this. Now, if you remember on the meandering river, the outside edge of the bends is always where it erodes the most. That is called your cut bank. The inside is where it deposits, and it creates what are called your point bars. So, and this is what accentuates the curve in these big meandering rivers. Okay, so remember, the outside where the erosion happens is the cut bank. The inside where deposition happens is the point bar. Any questions on that?
No.
Okay. All right, let's get this. All right, now let's hop back on over to this. Okay, so where does the most erosion occur in a meandering river? We just talked about that. On the, so you guys remember?
The cut bank.
Cut bank, right? Which is on that outside edge of the curve. So, what is a 100-year flood? So if you guys remember this, back from the reading and the guided lab.
Doesn't that pretty much mean that there's a 1% chance that a flood like that could occur in 100 years?
In a given year, not 100 years.
In a given year, right?
Yeah, that's right. So it's just a statistic. And what it is it's not super scientific at all. It's just looking back over the last 100 years, look at the largest flood, and then we say, okay, that's a 100-year flood. That means there's a 1% chance every year that a flood like that could happen. But why is that somewhat deceiving?
Because you can have more than one 100-year flood in 100 years.
That's right. And it's just because that's just a simple, non-scientific statistic. So, I've seen many cases where it'll go 99 years and there's no flooding. And then in the 100th year, there's 3 100-year floods, not 1, but 3. So, it just depends. And then there's sometimes when there's none. So, it's all just, relative. Okay. How can you tell the power capabilities of a river just by looking at it? Anyone? This is a little harder.
Is one of the ways the angle?
Yeah, the angle that it's flowing. So, for example, I'm going to show you one. A river coming down to the side of a mountain, those big fast rivers that have the big rapids and everything, that's a very powerful river. And you can see that in the angle and the rate at which the water is moving. If it's got waterfalls and stuff and whatnot. Whereas those big, big rivers in the Midwest going, just moseying on their way, aren't nearly as powerful. They're not pushing as fast and as hard. So that's one way. You can also tell, again, by just the speed of flow and depth and a lot of other things. But those are the 2 main ones: how fast it's moving, kind of the angle, and also just like what is it moving? Do you see a lot of cobbles and boulders, or does it have big sandy, or does it have big like muddy banks and stuff like that? Okay.
Mr. North,
Yep.
can I interrupt you really quick?
You betcha.
We're not able to pull up the class anymore. James just texted me.
Yeah, I know.
Saying he can't pull up the class anymore. Okay.
Kira was saying that too, and I don't know what's happening. I'm going to email the tech support, and maybe I have an email. I'll check in my email tonight too. There might be a chance that there is some type of weird maintenance going on. I don't know. I'm also going to talk to my supervisor, see if her class is experiencing the same thing, and we'll get this fixed, especially since I'm sure you guys want to get things submitted and also be able to have access to the final. So we'll get this fixed hopefully tonight.
Yeah, I was going to stay after and ask you because I didn't know if anyone else was experiencing.
Yeah, this seems to be a class-wide thing. I don't know if it's, and I'm going to contact other professors and find out if this is a class, like a course-wide thing or what. So, and I know they did just push an update through just the other day on Canvas, and I'm wondering if maybe there's something funky with that. Regardless, I'll look into that today, and we'll see if we can't get this all fixed out.
All right, because he haven't submitted the presentation, so let's just worry
and
about
don't
that.
worry. If you guys can't get on, I'm probably gonna change the deadline on, because I didn't know that this problem was happening until tonight. So probably tomorrow I'm gonna go and extend the deadline so that nobody gets dinged for late points or anything because of computer problems on BYU's part. So don't worry about it.
Okay. I'll send a message. Thank you.
Now, these 3 questions at the end, these are just for, make sure you know those with the case studies. So case study flood which was caused by an atmospheric river. Know which one that one was. Go back through your case studies. Which case study flood was the deadliest disaster in history? I mentioned that earlier, so rewatch the video and go back to your case studies. And then which case study was the deadliest flood in the US? So make sure, spend some time going through the case studies, spend some time going through those documents that I posted that have the answer to all these questions. And we will kind of wrap up now with hurricanes and tornadoes. So where do hurricanes, first off, any questions on flooding before we move on?
Nope.
Okay. If you guys think of any, that's fine. We can talk about them. Just let me know. So we'll go to hurricanes. Where do hurricanes get their energy? If you guys remember from the reading. Okay, so hurricanes get their energy from the evaporation and rising of the warm air and liquids along the equator, where they'll cool and come back down. Kind of creates this circulation. That's one part. Also, you get it from a couple other drivers with like winds and waves. Those can contribute, but it's mainly just the cause of the evaporation, kind of in those warm tropics. Okay. What is required for a hurricane to form? Do you guys remember that? You need warm, you need the evaporation, you need the circulation, kind of the movement and circling around it. There's a really good PowerPoint. Let me see. In the class, hopefully I have access now. Let's see. Well, it looks like I still have it, so hopefully I can pull it up. Maybe not. Okay. Let me pull up a PowerPoint real quick that really shows this good. Oh, come on. Right here. No, that's tornadoes. Yeah. Okay. Okay, so this presentation right here, I really like because it shows, oh, what in the world? It shows really well kind of what is going on to what you need if it opens. I'll have to give it a second. Okay. So right here, how to build a tropical cyclone or hurricane. Remember cyclone and hurricane. A hurricane is a type of cyclone. So you need a pre-existing disturbance. You need locations several degrees north of the equator or south, just depending on what hemisphere. Little change in wind speed, inner direction with height. So that's just kind of, as you're going up the air column, it should all be relatively uniform. Warm sea surface temperatures. Unstable atmosphere, so the temperature goes down as you go up, something just kind of wonky like that. And high atmospheric moisture content, so just a humid atmosphere. These are the drivers that kind of build your hurricanes. Okay, now let's see if you guys remember. What is the most dangerous and deadliest part of a hurricane?
The wind speed.
Not quite. That is very dangerous, but there's a more dangerous part. Anybody? Okay, let's see here. There's a really great pie chart on this very presentation that does a fantastic job breaking it down right here. So this right here is all the U.S. Atlantic tropical cyclone deaths from 1963 to 2012. Storm surges account for 50% of all deaths. So the storm surge is the worst, most dangerous part of a hurricane. As a matter of fact, just to kind of help you guys remember this, I want to show you guys a video. This video right here, he explains a little bit about storm surges. So we're gonna watch this, and I think this will help you understand. Can you guys all hear it? Okay.
I can't hear him.
I can't
No.
hear it.
Let's see. You guys can't hear. Let's put on subtitles. See if that does it. Nope. Shoot. Let's try something. Stop share. Share. Let's see. Okay. Can you guys hear now?
No, it's just the same.
No.
Okay, so he's talking about areas, and I'll just kind of walk you through. He's talking about where some storm surges can occur, you know, some risk zones. But what I want to do is skip forward to right here. So right here, he's talking about relative. This is a 3-foot storm surge. So this is a relatively small, for some of the areas to be hit. That's what a 3-foot storm surge is like. At this point, when you have a storm surge that's 3 feet tall, your house, you have to be on the 2nd level. You cannot get out. You are stuck. Now you can get a 6-foot storm surge. This is at 6 feet. Here, you absolutely have to be on the upper floor. You probably are on your roof at this point because the 1st floor is completely inundated. And then he's going to show you here you can get a storm surge in this hurricane of 9 feet. This is a 9-foot, basically, tsunami that comes through with the hurricane. And that's how much water it moves in. At this point, there is nothing you can do. You have to be on your roof. And if you're on your roof, you're probably getting blown off the roof because of the winds into the water. One of the risks with these storm surges is like a tsunami, the water has to go somewhere, and after a while, it goes back out to sea. So these storm surges will actually carry most people out to sea, and they'll drown if they haven't already drowned. Okay, so let's stop share. Let's just do desktop share. Okay, so your storm surge is your most dangerous part of a hurricane. As a matter of fact, the largest storm surge ever recorded was 33 feet.
Oh, wow.
Okay. Where do hurricanes occur in the U.S.? You guys remember? Where do they mostly hit?
Aren't most of them either happening in the Gulf or on the kind of the south and east coast?
Yeah, so and that's perfect. I want to show you the presentation again.
And I think there are some in California, but not nearly as many.
Yeah, and they usually trip. So if you're, I don't know if you guys remember from the reading, typically your cyclones track from east to west. So a lot of times the stuff that California gets tracks over from the Gulf. Okay, let's see. Might be at the very end is the best figure I'm thinking of. No, okay, sorry guys, don't get sick while I'm scrolling like a madman here. Okay, so this kind of shows a good track here of these tropical cyclones. They mostly come up here hit the Gulf, Florida, Carolinas. That's kind of this kind of area right here is the region in the United States that gets the most hurricanes or major tropical cyclones. Now, as we know from Sandy, they can go up into the East Coast, hit New York and other places, New Jersey and other places like that. But really, the predominant zone is right here, this southern belt. Okay. And again, that just all has to do with a lot of your hurricanes forming right here, kind of off the Cape, the coast, off the coast of Africa, and the way they blow in. Okay, go back to this one. Okay, what does the Saffir-Simpson scale measure? So this is this scale right here, and it's kind of easy to see. So it looks at wind speed and damage at windfall. So your category 1 and 2 hurricanes have the lower wind speeds of 74 to 95 miles per hour and 96 to 110 miles per hour, where they have minimal to moderate damage. Your major hurricanes, which are categories 3, 4, and 5, have significantly higher wind speeds where extensive damage is done. It's mostly the damage they look at right here. Okay, storm surge, we talked about that. Okay, where are some safe places to be during a hurricane? If you guys remember.
Well, I think with how good the warning systems are nowadays, you can be well away from a hurricane, like not even near where it's going to make landfall before it hits.
Perfect. And that's like the perfect answer, right? The safest thing to do in the event of a hurricane is to simply leave. What were you going to say? Someone else was speaking.
Oh, I was just thinking in a basement or somewhere. I was thinking, if you were indoors.
Now, would you want to be in a basement? Because you get flooding and a storm surge.
Oh, no.
Nope. Typically, you want to be, if you're in a region with storm surge, you probably want to be out away from the storm surge. If you're in a region that's in the storm surge and you haven't evacuated, that was just a really poor decision on your part. If there's no threat of a storm surge, you want to be away from your windows, kind of in towards the center, a room without windows, just a kind of a solid section in the center of your home. Okay, now with the tornado, where do you want to be?
So that one, if you have a kind of a storm cellar,
yeah,
it would be a good idea.
Yeah,
and also I was actually surprised to learn that just being outside flat on the ground,
yeah, it's very safe.
fairly safe too. Yeah.
That's right. You know, I remember growing up, under the impression growing up as a kid that if a tornado ever comes, and you're out driving, you need to get to the nearest underpass.
Yeah.
But no, you find a ditch and you lay down. And if there's no ditch, you just get out of the car, get as far away from as possible, and lay down. All right. Make yourself as close to the ground. The wind has a lot less place to pick you up and throw you away, and you're a smaller target for flying debris. Yep. And then obviously a storm cellar, or in a basement. If you don't have a basement, in a good solid bathtub that's in the center of the house with mattresses piled over the top of you. So yeah, and then some other things. What are some different names for hurricanes around the world? So in the Indian Ocean, do you guys remember what they're called?
Let's see. I know there was
Cyclone.
Cyclones.
Yep.
Typhoon.
Yep.
What else? Those are the ones that I remember because the recent what do you call this, natural disasters that I was going through.
Yeah. Yep. So cyclones, typhoons. Man, now I'm drawing a blank. You've got.
Tempest one of them?
I can't remember. I can't remember either. Let's see. Tropical waves. This is all about the mechanics of it. Might be the other presentation we need. Let me pull it up on the other presentation. That way we can go over them all again together, because now it's going to bug me that I can't remember them. Okay. Oops. Cyclone. Let's see. Okay, here we go. typhoons and cyclones and hurricanes. So that's just the three. Typhoons are kind of in the South Pacific, or in just in like the Pacific, like, and then cyclones once you get over into the Indian Ocean. And then hurricanes are the Western Pacific, kind of over here coming off of California, and then in the Atlantic.
Brother Northrop, just a
Uh-huh.
question.
Uh-huh.
Why is there like different names for it, although they are all similar?
You know, I don't know. I don't think there is a good reason, because, and you'll notice this at the beginning of the PowerPoint up here. I think it's right here. Right here, hurricanes, a tropical cyclone with maximum sustained winds. It's kind of just denoting those. In the western northern Pacific, hurricanes are typhoons. Similar storms in the Indian and South Pacific Oceans called cyclones. They're the same thing. I think it's more just region specific. Just kind of denoting, hey, it was a typhoon. Okay, that means it's in the Far East, you know, in the South Pacific. I don't know if that kind of makes sense. That's the best answer I have. I don't think there's a real scientific reason for it. Okay, so now just go back through the case studies, which was the costliest hurricane, which was the costliest tornadoes, which U.S. hurricane was the deadliest, which U.S. tornado was the deadliest, which U.S. hurricane had the highest wind speeds, and which 3 hurricanes have been Category 5 when they made landfall in the U.S. And that's that one. Look in your guided labs. So what I'm going to do is probably tomorrow, because tonight I'm going to try and figure out what's going on with your guys' Canvas. But tomorrow, you guys, I'm going to post the case studies document that I always post that has all the answers. You guys can also use that, okay? All right. Any questions on hurricanes and tornadoes?
Nope.
Okay. Any questions on anything in general? Anything anybody wants clarification on?
I just wanted clarification on the presentations.
Mm-hmm.
For the final product, the whole group had to submit the same presentation, correct?
Yeah. Mm-hmm.
Okay.
And you know, if they vary a little bit from person to person, I don't knock too much. I do see that sometimes, but it should be relatively cohesive because it is a group. So,
Okay.
perfect. Any other
That's
questions?
what I thought.
Oh, sorry. Yeah, I didn't mean to interrupt you either.
Oh,
Yeah,
no.
no.
It's going fast anyway. Your speed is like flying. I don't know why on my computer.
Oh, I'm sorry.
No.
Okay, anybody got any other questions, anything?
I do have a question about, so do we have access to the previous tests we have taken? So like, can we
Yes.
look, so would those be good things to use as guidelines?
I think that is a fantastic point. Yeah, that would be a great place to go to just kind of review, because those test questions, I guarantee they're probably going to be recycled a little bit as well. So you can go through, study what you did. So I think that is a fantastic option. And I know I think actually most of you guys missed the very beginning. So I'll just kind of reiterate it here. One thing you guys can do for your extra credit, go back through your old tests, and this is a great way to study as well. Look at when you open it up, I think you go in and you just click on the test, and it'll like where you submitted it, and it'll pop up and it'll show you what you got right, and then it'll also show you the answers you got wrong, but it won't give you the correct answer. If you go through all the answers you got wrong and then put in write me a paragraph why that answer is wrong and what the correct answer is, and you do that for every answer you got wrong on all your different tests, and then send those documents to me, I'll give you half credit back on all of those problems.
Oh, wow.
So I don't care about the tests. I just want you guys to learn. So, do that. You can get you know, if you're at a 50%, you can end up with 75 on every test. So, and it's a great way to study. So that's an option for you guys. But yeah, you have access to those. I think you just go and look, you can just click on where you submitted it and it'll pop up and you can see your results. And not your just results. It like goes every question, what the answers were, what you selected, and if it was right or wrong. So great question.
Well, at this present, oh, go ahead. At this present time, sorry, I don't have access to the class at all. So
Yeah, no, I don't
days
think
it's
anyone does. I don't know what is happening. I'm gonna, like I said, I'm gonna send out some emails tonight, let IT know, reach out to professors, find out if they're having that same problem, let my supervisors know as well. So hopefully we can get this solved before tomorrow so you guys can get on and start studying and do the things you need to do.
Okay.
So any other questions?
Okay. Well,
Okay.
just
Well,
got back from vacation.
so now you're just trying to get back.
I'll catch up.
Yeah.
Yeah. I'm trying
All
to
right.
get in the
I'm
flow.
going to stop the recording now.